Good morning, everyone, and welcome to today's webinar, ModSecurity 3.0 and NGINX Getting Started. I would like to introduce today's presenter, Owen Garrett, who is Head of Product at NGINX, and will take you through today's webinar. To ask any questions, please submit them via the question box, and Owen will answer them at the end of the webinar. Please note, a recorded version of this webinar will be available after the event. I would now like to hand you over to our host, Owen.
Good morning, folks, and thank you very much for joining us today as we talk about NGINX and its integration with ModSecurity. Over the next half an hour, I'd like to share with you some insights on the current security landscape, so issues that you may be seeing with the applications that you're running now, and issues that your colleagues and other websites have observed. We'll talk about ModSecurity and its role as one of the pieces of technology that you can deploy to protect your website and web application and online services from malicious traffic and hackers. And then we'll delve in to the process that you would go through to build, compile, and deploy the ModSecurity open source web application firewall with NGINX open source. NGINX also provides a pre-built ModSecurity module for NGINX Plus, our commercial product, and we shall touch on that and compare and contrast the installation and deployment processes. And then we'll go in a little bit more detail and look at the basic configuration that you would go through to configure ModSecurity to inspect and begin blocking suspect traffic to your website. Let's begin by looking at why security is important for the modern web application. Akamai, who manage and operate one of the world's largest CDNs, track and profile the traffic that their CDNs observe in order to determine trends in internet traffic. Each quarter, they publish a report looking at the kinds of security issues, the patterns, the attack patterns, and the vulnerabilities that they see happening in the world. And over the last 12 months, they have observed a significant increase in the number of attacks that are specifically targeted against modern web applications. These are Layer 7 attacks, HTTP and HTTPS requests that explicitly attempt to exploit vulnerabilities in the application itself. Whereas they observed that over the last 12 months, there had been very little change in the level of distributed denial of service attacks against web properties. Attacks like DNS and SYN floods that seek to overwhelm an application or a service simply with volume of traffic. In fact, if anything, they saw a very slight decrease in total denial of service attacks against the properties that they were responsible for managing. And from this, we can infer that there is a step change in the kinds of attacks that hackers and malicious actors are mounting in order to take websites offline, to steal sensitive data, and to compromise the operation of businesses. If we focus in to just the last 3 months, Akamai observed that there was a 30% increase just over the last 3 months in total web application attacks. This would be a mixture of scanning and reconnaissance attempts run using popular open source, easy to obtain scanning and vulnerability checking tools, through to very specific targeted attacks at a particular property where an earlier reconnaissance has indicated that that property may be vulnerable. And these attacks are spread across every major industry. Of course, there's a heavy preponderance towards investigating and attempting to exploit retail, gaming, financial services, and high-tech sites. Sites where the opportunity is larger, the goals, the prize is greater should you be able to either compromise the site or take content. But it's important to point out that these attacks cover the entire gamut of websites, through from high traffic retail to lower profile but equally sensitive business service sites. Attackers are after a range of different information or resources or opportunities as they seek to exploit a website or web service. They may be looking for high-value personal data. By being able to tie together credit card records, passwords, and other identity information, an attacker can build an online profile of your online and offline activities, which is incredibly valuable should they seek to sell that information on to someone who is trying to operate some sort of identity theft operation. And this kind of information, once validated, is available and distributed widely across the dark web. But there are also examples in recent months of attackers who are seeking to extort information or extort money from individual websites or web applications. Uber, for example, were vulnerable to an attack where a large number of user details were taken, and they ended up paying off the attacker on the promise that the attackers would delete the information that they had stolen. Other attacks seek to encrypt sensitive data on a Linux or Windows server and then make a charge. Linux Encoder was a recent attack that did this in an attempt to make a charge, often through bitcoins, to provide the decryption key for your data. Attackers may simply be looking for vulnerable systems in order to co-opt those systems into a botnet or to use them for cryptocurrency mining. And finally, one of the longest term trends across the internet, attackers have always been seeking to exploit websites and web applications in order to drive their own agenda for political change or in other ways to damage the business reputation of a web property. Is this a widespread issue? Well, just in the last 8 months of this year, over 232 million people have been affected through information disclosure for payment details, for usernames, for passwords, for addresses. 232 million people affected. That's not including the 3 billion Yahoo account details that were leaked over the last couple of years and to which Yahoo finally admitted to in October of this year. As a personal recommendation, I'd strongly suggest that you go to one of the websites that hosts and provides a front end to some of this data. HaveIBeenPwned.com, for example. Put in your email address and it'll give you an indication of where that email address has been found in publicly disclosed dumps of data from hacks of websites and web applications across the world. It's a chilling reminder as to how sensitive and vulnerable we can all be to this kind of data leakage. And all of these attacks, all of these vulnerabilities were tracked back. These were only the disclosed data breaches, of course. Although organizations in most geographies are legally required to disclose if data has been leaked, of course, many organizations will sidestep that or be a little bit reticent in admitting to an attack. But all of these breaches and leaks relate to vulnerabilities in the technology that was deployed in the web or payment stack for these services. As an operator or an owner of an online service, what can you do to defend yourself and reduce and minimize the risk of your website or your web application being subject to this kind of attack? It's a challenging problem. There is no silver bullet, and enterprises will typically deploy a multifaceted, multi-tier approach. Many, not all, but many will begin with some sort of distributed denial of service protection that will help to protect their application from volumetric-based network floods. Some of the more sophisticated CDNs provide this as part of their service. So from their POPs located across the world, they will make an attempt to soak up and block volume-based attacks. But these are of limited effectiveness because, of course, many application-level attacks cannot be distinguished from real application traffic at this part of the infrastructure. So attacks need to be let through. And also, a smart attacker can easily bypass the front-end CDN and send their volumetric attacks directly to the vulnerable web service. And so that takes us to the types of technology that you should consider deploying in line to manage, inspect, and block traffic within your data center, whether it's a physical data center or you're running on a cloud like AWS, Azure, or Google. At the very lowest level, you would protect yourself from protocol level attacks, things like SYN floods, by using a network firewall. A network firewall typically operates at layer 2 to 3 in the OSI network stack and is configured with a whitelist of traffic that it will permit. So, for example, traffic from internet locations is permitted to access the front-end load balancer for my web application. And they may also be extended further with explicit blacklists, banning particular types of traffic. But in general, these devices are configured with a whitelist, what traffic should be allowed, and anything which fails to match those whitelists is automatically denied. It's a little bit like a ticket booth or a ticket checker coming into an organization site, verifying that a user has an appointment, has a destination to go to, and they're permitted. In the next level up, you may wish to deploy a separate IPS, intrusion prevention system, or this may be integrated with your network firewall. An IPS is able to inspect traffic flows up to layer 4 and identify anomalies. It's not often as relevant for web applications, but it's critical if you're running some sort of branch office or business operation behind a gateway, in order to detect if unexpected traffic is happening. There's a sudden spike in SSH traffic from the internet to a particular server, for example. An IPS is effective at identifying these anomalies, effective at spotting common signatures at a network layer for particular types of traffic. But these two devices, firewalls and IPSs, are both ineffective at inspecting traffic, particularly when the traffic is encrypted using SSL or TLS, at inspecting that traffic in order to determine if the payload of that traffic is in some way malicious or dangerous. And for that purpose, you need a system like a web application firewall, operating at layer 7 in the network stack. A web application firewall is generally deployed as an add-on to a load balancer or application delivery controller, and it includes a range of signatures that attempt to match traffic against known bad patterns. Injection attacks like SQL injection, cross-site scripting, application misuse, brute force attempts to attack a login page. The web application firewall is generally deployed on a per application basis, or at least configured on a per application basis. And it's very, very specific for that use case. So generally, a web application firewall is effective at protecting HTTP and HTTPS-based services from these attacks. In addition to these inline devices, you may also wish to consider static analysis tools, app security testing tools, and dynamic app security testing tools. Static tools inspect source code for applications, identify potential weaknesses, wrap whitelists around certain bits of input, and can be used to generate web application firewall rules. For example, a SAST tool may identify the particular request parameter corresponds to an email address, and so would create a web application firewall rule that ensured that the only data that goes into that request parameter is plain text and where appropriate looks or appears to be an email address, thus blocking things like injection attacks or binary injection for that form parameter. And DAS tools, dynamic application security testing, look to monitor the application in real time as it runs, identify errors, and then potentially mount an asynchronous penetration test against a component of the application that's failing in order to probe it to determine if the errors that are being seen are in some way revealing a vulnerability in the application. These DAS tools can similarly generate web application firewall rules that can be deployed on the WAF to protect parts of the application that have been detected to be vulnerable. Let's look at an example vulnerability and how a web application firewall could be used in real life to protect against the effects of that vulnerability. And we're going to pick the Apache Struts vulnerability, CVE 2017-5638. This vulnerability was the one behind the very, very widely reported Equifax breach that resulted in 143 million client details being retrieved from Equifax's services. And as an end user, the first place where you would typically learn about a vulnerability of this type is through a CVE publication from NIST or other organizations. In the case of Struts, Struts is a Java library that implements an MVC, Model View Controller interface for Java web applications. It's very, very widely deployed. It's deeply embedded within Java application frameworks. It's not shipped as an operating system library. It's shipped as part of an application. And this makes it very, very difficult to audit and to update when a vulnerability is found. It's owned by individual application teams. It's bundled with the application. And it's very difficult for the network operation team to scan systems to identify whether that vulnerable Struts version is deployed. Individual applications would need to be patched, tested, and then redeployed. And many of these applications may be several years old, using old versions of Apache Struts, potentially pulled in through external dependencies. So the application team may not even be aware explicitly that a particularly vulnerable version of Struts is being used by that application. In the case of Struts, the vulnerability was subtle, but relatively easy to exploit. It came from incorrect exception handling. When the Struts framework saw a particular HTTP header of an unexpected type, so this was either a content type, disposition, or content length header. When that header was an unexpected value, the Struts framework generated an exception and an error message. And the issue was that the error message took part of the data and treated that as what Struts calls an OGNL expression. It's a message which corresponds to a piece of code that needs to be run in order to generate the true output. Attackers were able to exploit that by embedding OGNL expressions within a content type header, specifically the hash command equals part of that expression. That would trigger the exception handling. The Apache Struts application would then execute that expression in order to generate the error message, and an attacker could subvert that process to execute operations, query a database, remove sensitive files, pull information off the host system, and to do that with the user of the Java application server. Within hours, attack tools and vulnerability scanners had been updated to test applications, to probe them, to determine whether they were vulnerable to this particular issue. And users reported seeing reconnaissance traffic across the internet as these automated tools started probing vast numbers of websites and web applications to determine if they were vulnerable to this particular fault. As an end user responsible for a web application, how should you respond once you become aware of a vulnerability of this type? Using ModSecurity, what we would recommend is that as you track these notifications, inspect and understand the nature of the vulnerability so that you can then determine what an appropriate response would be. In the vulnerability announcement, it was described as being exploited with a content type header containing a hash command equals string. With that information, you can very easily create a suitable ModSecurity web application firewall rule that will block traffic where the content type header contains that suspect string. And as a very, very first step, you would then deploy that rule on your production web application firewall, and you would monitor the effect. Track your logs, determine if there's been an increase of blocked traffic, and where traffic has been blocked, verify that it is indeed attack or reconnaissance traffic, and instead you're not affecting the correct operation of your web application by creating false positives. Then, having quickly deployed that rule in response to the vulnerability announcement, look into it further. Work with the community, understand what the open source community is doing to address this issue and the recommendations that are emerging around ModSecurity. For example, as you read that further and investigate further, you'll realize that more headers can be used as a vector for this vulnerability, and additional OGNL expressions can also be used. So, on reflection, you may wish to increase the security further by adding additional web application firewall rules. By doing this relatively quickly and easily, that then buys you time to audit, check, update, retest, and redeploy vulnerable applications. And once you have done so and verified that those applications are indeed invulnerable to that particular Apache struts bug, at that point you can safely decommission the WAF rule. So a web application firewall is not a panacea for application bugs, and it's not the only way, the only point of control. Ultimately, you should always look to fix the application bug that the application firewall is protecting you from. But it does buy you time, and it does give you a belt and braces second level of support to protect against vulnerable traffic. And using the rules like SQL injection is a wise move in order to protect you from known malicious traffic, whether the application is vulnerable or not. So we talked about vulnerabilities, we talked about ways to protect against those vulnerabilities, and I alluded to ModSecurity. ModSecurity is the most widely deployed web application firewall on the planet. It's an open source project. It was first released in 2002, around about the same sort of time that NGINX was first developed. It was developed by an engineer called Ivan Ristic, who made the pragmatic observation that to fully secure a web application was a fruitless and impossible task. By inspecting and ensuring the code was 100% solid. And instead, he realized it was necessary to put some sort of tool in front of a web application to protect it from known and suspicious kinds of traffic. And that became the genesis of the ModSecurity project. You can regard it a little bit like a virus scanner, but for web applications. It understands what appears to be bad behavior. It is preloaded with a large number of signatures for what is known to be bad traffic, and it protects the application by blocking both bad behavior and traffic that matches those signatures. ModSecurity is a mature product. It has gone through a number of releases. The most recent release, the 3.0 tree, came earlier this year. And we'll talk about that and its relevance to NGINX in a couple of slides. So what is ModSecurity? It's a dynamic module for NGINX. It can also be run with other reverse proxies and web servers like Apache and IIS. In the case of NGINX, it would typically be deployed in front of application servers. NGINX operates as the bump in the wire, inspecting all network traffic, and it's an ideal location in which to insert ModSecurity web application firewall rules. You would configure NGINX to pass certain or all of your traffic through to ModSecurity for inspection, and ModSecurity matches that traffic against a database of rules, just like the Apache struts rule we saw earlier on, searching for malicious patterns. You can then configure ModSecurity to handle matching traffic in a range of different ways. Drop it, maybe permit it, but log it, or route it to a honeypot. With ModSecurity, you get a set of rules that provide you with sophisticated layer 7 attack protections, protecting against things like SQL injection, cross-site scripting, attempts to do cross-site request forgery. It integrates with the project honeypot project, with the honeypot project for IP reputation. It implements the standard regex rules language, PCRE regex. We saw that in use when we were matching against the command equals and commands equals patterns in our Apache struts example. It integrates with a range of third-party tools. These tools are able to operate as static security analysis tools or dynamic application security analysis tools to generate ModSecurity rules, which you can then deploy on your production systems. ModSecurity provides very, very detailed and verbose audit and debug logs, and it can be deployed alongside a range of other technologies and measures in an environment in order to meet the requirements of the PCI DSS standard. Specifically, section 6.6 of the PCI DSS standard talks about the need to deploy a web application firewall as an alternative to conducting regular code security scans, to deploy a web application firewall to protect against common web vulnerabilities. I explained that ModSecurity is a long-standing project, first released 15 years ago in 2002. ModSecurity began as an Apache module. The architecture and the implementation of the ModSecurity project was very, very tightly aligned to the internals of how the Apache web server project was implemented. ModSecurity was available for other web applications. It could be built and deployed within NGINX and within IIS, but at the previous to the 3.0 release, it could only be deployed in an Apache-like fashion, where it implemented the Apache interfaces, and then there was a string and sealing wax approach to translate the NGINX or IIS interfaces through to Apache-like ones. This caused performance, reliability, and availability issues. It was a fragile and unreliable solution. With the version 3 release, the TrustWave team, who were responsible for ModSecurity, worked with us, with NGINX, to extract the core ModSecurity functionality into a standalone library, libModSecurity, and then to implement dedicated connectors that translated between the NGINX API to the standard libModSecurity API. And connectors are available for other web platforms as well. Apache and IIS are in progress. And so, the previous ModSecurity 2.9 technology technically worked, but in an unreliable and low performance fashion with NGINX. With libModSecurity and the integration through the connector, you get a much higher performance, much more reliable implementation of ModSecurity. And this will be the future of ModSecurity. Future developments will go into the 3.0 implementation and beyond. NGINX are actively participating in this project. We have a support relationship with Trustwave, and we work with them to ensure that their implementation works as best as possible with the NGINX reverse proxy and web server. ModSecurity 3 has a couple of caveats in relation to ModSecurity 2.9. A couple of the rules are not yet supported by version 3, the DDoS rules in particular. This is less of an issue when you use with NGINX, because of course you can use the NGINX native functionality to inspect and protect against volumetric-based attacks. Currently, rules that inspect responses are not supported within ModSecurity 3. Again, with NGINX, you can use modules like the text substitution module to inspect, to find response data that, for example, looks like a credit card number, replaces that. So that can be done without needing ModSecurity. And there's a small number of other miscellaneous directives that were specific to 2.9 and the Apache integration that the Trustwave team are not planning to carry forwards. That said, the OWASP rules developed by the OWASP community and Trustwave's commercial rule set are both fully supported by ModSecurity 3, whether running on Apache or running on NGINX or other web platforms. So how would you go about getting started with ModSecurity with both NGINX open source and NGINX Plus? If you use NGINX open source, then you will need to build, compile, and link ModSecurity from source. You can take the source directly from the Trustwave GitHub account, and the instructions that I'm going to share with you are published on that GitHub account. So this is the place to begin if you're taking a fully open source approach. First, install NGINX from our official repository. You could potentially also use NGINX binaries from your operating system vendor's repository if they've been compiled with the correct flags and the module build process works. So your mileage may vary. We tested and we strongly recommend that production NGINX systems use the binaries that are shipped from our mainline tree, because those will be the most up-to-date, both in terms of features and bug and security updates. And then install the necessary prerequisites so that you're able to build the ModSecurity module. First, we're going to build libModSecurity by cloning the v3 master branch from the ModSecurity repo. Build it, configure it, make install. That will build the standalone libModSecurity.so module and deploy that on your system. And then we're going to deploy the NGINX connector. It's a separate body of code. Pull it from the ModSecurity NGINX repo. We're going to build this as a dynamic module for NGINX open source. And so the way that we do that, it's well documented on our blog, is we determine the deployment version of NGINX that we're going to use, in this case 1.13.7. We grab the corresponding source code for that version. So remember, we don't need to rebuild NGINX in this process, but we do need to grab the source code so that we can build the module and link it against the correct headers, so it has the correct ABI compatibility. So we grab the source code. We then configure the source code with the ModSecurity NGINX module that we obtained from GitHub. We make the module's target with the NGINX source code. This won't build NGINX, but it will build the additional modules that you configured. And then we can take that module, NGINX HTTP ModSecurity module.so, and copy it to the standard module location in your NGINX deploy, etc. NGINX modules. This is the process that you can go through to take the current build of ModSecurity from GitHub, build libModSecurity, build the NGINX connector against your deployed version of NGINX, and then deploy it. For our commercial subscribers who take our NGINX Plus binary, we provide a managed and maintained build of ModSecurity. This brings a high degree of convenience. You don't need to build it yourself. And it also brings a curation from our NGINX team. When we build the module, we test it explicitly against the commercial build of NGINX, i.e. NGINX Plus. It runs through our test system. We monitor the ModSecurity tree, and we decide when it's necessary to make updates to the ModSecurity module, and we proactively push that out to our NGINX Plus subscribers. So, as an end user of NGINX Plus, deploying ModSecurity is relatively straightforward. You can take it directly from our module repository, the same location that you obtained the NGINX Plus binary from. It's simply a matter of apt-get install, the module package, and for information, we also ship a range of other third-party modules with NGINX Plus, and they're all deployed in exactly the same fashion, pulled directly out of our module repository, and they all benefit from the build and deployment testing that we conduct whenever we make new NGINX Plus releases. Having obtained the module and deployed the binary in etc. NGINX modules, then you need to get started by configuring NGINX to load the module and to use some simple ModSecurity rules. The process is identical whether you're using NGINX open source and have built the module yourself, or whether you're using NGINX Plus and you're using the module that we have built. It's well documented on our website. You can hit the admin guide for NGINX and follow the instructions on build, deploy, and configure. The admin guide talks through creating a simple web application and then creating a simple ModSecurity rule to block particular traffic so that you can then verify that ModSecurity is operating correctly. To do so, the very first thing that you would do is edit your NGINX configuration to load the dynamic module. Then, when NGINX is reloaded, or its configuration is restarted, or its configuration is reloaded, the NGINX worker processes will pull in the dynamic modules listed with the load module directive, and the functionality in those modules will then be available to you through the NGINX configuration. The ModSecurity module exposes a number of additional directives that you will then use to configure ModSecurity to inspect and block traffic. ModSecurity is bootstrapped with a basic configuration, modsecurity.conf, and you can grab a sample of that basic configuration from GitHub using the instructions here to take the TrustWaves or the Spider Labs ModSecurity config, deploy that on NGINX in somewhere like etc. NGINX ModSec. And for this example here, we're going to make one change to that configuration. At the bottom of the screen, we're going to change the sec rule engine and policy from detection only to on. With detection only, we log suspect requests, but we take no action. When it's on, we log and we apply the configured action, which would typically be to block the request. We're going to do this for test purposes. When you deploy this in production, it'd be wise to first deploy it in detection only and monitor the logs to determine whether any false positives are being generated. So, follow the instructions on our admin guide to get hold of the master modsecurity.conf configuration. Make this simple change, and then we're going to edit our main.conf, and we're going to pull in both the modsecurity.conf we took from TrustWave Spider Labs, and we're going to add a basic test rule. This test rule is the last line in this configuration. It's a security rule that runs against the arguments, so the query string or form parameters arguments. It's going to run against an argument called test param, and if that argument has a value that contains the string test, then we're going to deny that request, returning with a status 403. We can then very easily enable this for a particular server on NGINX. So for a particular server, we turn on ModSecurity and we pull in the main.conf file that we showed on the previous slide here. Reload NGINX, so NGINX -t to test the configuration is correct, -s reload to reload it, and then we can test it very simply. Issue request with a query string with an argument called test param and a value called test, and you can see that we're receiving a 403 forbidden response. This response is being generated by ModSecurity because the rule that we added has been triggered by this particular request. The action was then to generate a 403 response. Having done that, the next thing that you would wish to do is to configure logging for ModSecurity so that you can begin to track what requests are being denied, and you can make an informed decision as to whether those requests are indeed malicious requests or are false positives. Because there is the risk that as you deploy ModSecurity rules, they could start blocking legitimate traffic to your web application. All blocked requests are logged to the NGINX error log at the warn level. So by default, you will see blocked requests. The error log report includes a message describing the ID of the rule and the reason why the request was blocked, so you can quickly match the blocked event back to the rule that triggered it. But if you need more detailed debugging, you can turn on the ModSecurity audit log. The audit log provides much more data about the internal processing of ModSecurity, of the requests that matched, and how ModSecurity built a score and decided the action to take on that request. And you can also turn on the debug log. The debug log may be useful if you're building particularly sophisticated ModSecurity rules. It provides a huge amount of internal data about how ModSecurity is managing and processing each individual request. You certainly should not turn the debug log on in production, and you may wish to think carefully before turning on the audit log in production, because they both generate very large amounts of data, particularly with large volumes of production traffic. Enable logging to your satisfaction, and then consider deploying the first ModSecurity rule set. OWASP is the Open Web Application Security project, and this project maintains a set of ModSecurity rules called the CRS, the Core Rule Set. The CRS is hosted again on GitHub. You can download that rule set and apply it to the NGINX deployment using the ModSecurity. Again, I repeat the advice. I would strongly recommend deploying this in a test environment or in production in detection only. Look for false positives. Make sure to monitor the performance impact of these rules. You may find that you can safely disable or bypass a large number of these rules because they may be looking for vulnerabilities which you know that you're not subject to. And in particular, if you do find that a particular named rule is causing an issue, you can very easily disable that rule with a simple ModSecurity statement, set remove rule by ID, add that to your main.conf, and then you can disable the named rule. So that is enough to get you started with ModSecurity. In review, there were two ways that you can deploy ModSecurity with NGINX. You can take the open source approach, where you take ModSecurity from GitHub and follow the instructions on GitHub that we shared to build, test, and deploy that module on your production systems. As updates are made available on the GitHub repo, then of course the obligation sits with you to track that GitHub repo, and where critical updates are made to ModSecurity, then you need to make a call as to when you build and redeploy those updates. Support, there is a rich community support on GitHub and Stack Overflow, and you can also talk direct to Trustwave and get commercial support for Trustwave's commercial rule set and for specific professional services projects to configure ModSecurity for your particular application. Of course, as open source technology, the headline cost is free, but the hidden cost is the obligation on yourselves to support and maintain the ModSecurity deployment. As an alternative, our NGINX Plus commercial subscribers can also subscribe to the add-on ModSecurity module. It comes at an additional cost on top of NGINX Plus, and with that you get fully tested ModSecurity builds from our engineering team, the people responsible for creating the release builds and binaries for both NGINX Open Source and NGINX Plus. We track GitHub. We work directly with the Trustwave support and professional services team to determine when it's necessary for us to push out updates to ModSecurity. And when that is necessary, we will create and test and deploy new builds and proactively notify all of our subscribers with information on the ModSecurity update. We partner with Trustwave to provide commercial support. The NGINX team provide commercial support around the deployment of ModSecurity with NGINX Plus and the basic configuration, setting ModSecurity up to use the OWASP CRS core rule set or to use Trustwave's commercial rule set. Trustwave can also provide professional services and support on a separate basis to help you configure ModSecurity in detail, specifically for your particular web application. And there is a cost to that. It's an add-on to the NGINX Plus commercial subscription, charged on an annual basis. And so, in conclusion, the number of web attacks that both popular and lower profile websites are facing is increasing year on year, with, as Akamai reported, a 30% uptick just in the last 3 months. The cost of a security breach can be devastating. The financial cost, the operational cost, and having to inform all of those people, all of the individuals who are affected by the breach, can be very high. The reputational cost, of course, is significant, and the internal cost to you and your colleagues of managing the fallout from that security breach can be very high. There is no silver bullet for protecting web applications. As Struts has illustrated, they are getting more and more sophisticated. There is a much greater attack surface, many more opportunities for attackers to attack a web application, and so a multifaceted approach is necessary. The most widely deployed web application firewall, ModSecurity, now runs natively within NGINX, either as an open source build or as a pre-built and pre-tested build with NGINX Plus. And NGINX Plus users get full support and particularly 24/7 support for that deployment. So, thank you all very much for your time. I hope this has served to be a useful introduction to ModSecurity and has presented some options to you for how to protect potentially vulnerable web applications. In the time remaining, I'd love to throw this open to questions. I'll pause briefly and pass back to Stephen, and Stephen can reshare the information on how to share questions with our team.
Thank you, Owen. To submit a question, please use the questions box on the GoToWebinar control panel to the bottom right.
Thank you. So, folks, if you have any questions from this webinar, please do share them that way. Several have come in already. First, what is the best way with a ModSecurity installation to update that installation when you've compiled it from code? So in that case, if you're running NGINX open source and you've compiled from code, you need to rebuild two components. You need to rebuild the lib ModSecurity module, and you need to rebuild the NGINX connector. You can deploy those on the running system. Fortunately, with Linux environments, you can overwrite critical binaries like that relatively safely, because the running applications will continue to use the old binaries. So what I would recommend doing is rebuilding and then deploying those binaries on the production system, and then reloading NGINX. At that point, NGINX will pick up the new binaries, both the new lib ModSecurity and the new ModSecurity connector. Do test it, of course, on a test system before you do that in production. With NGINX Plus, we package those libraries as part of a deployable package, and so the operation of deploying those libraries is implemented by the deployment scripts in that package. Can logs be stored in JSON? The ModSecurity logs are kind of JSON formatted. ModSecurity predates JSON standards. There are a range of open source tools and commercial tools that are able to interpret those logs, or you can build your own scripting which will take those log files and then pull out the data that you need. They're structured in a way that's easy to machine process, but they're not quite JSON. Do you provide a set of rules as part of NGINX Plus? So no, we don't. We provide the NGINX Plus binary, and we provide a pre-built version of ModSecurity, and our support team are able to work with you and interface directly with Trustwave on your behalf to help you use ModSecurity. If you need rules, your options include using the CRS, and we'll provide support on deploying CRS. You can subscribe to Trustwave's commercial rules, and those are fully supported with NGINX Plus and ModSecurity. And there are other tools and other sources of rules as well that you can lean on. Apart from the cost, someone asks, what would be the advantage of running NGINX and ModSecurity instead of a solution based on something like Palo Alto, next generation firewalls with threat prevention, or F5 Big IP with ASM? So I won't talk specifically to individual competitors or alternatives, but I want to reiterate a couple of points. First is that security needs a multifaceted approach. Absolutely, you should be deploying some sort of network level firewall device and intrusion prevention system in addition to a web application firewall. A web application firewall is only capable of inspecting HTTP requests and blocking those. It's not designed to do other types of security measures. In terms of comparing with other solutions, ModSecurity is mature. The Trustwave rule set and the OWASP CRS are used as sources for rule sets for a number of commercial web application firewalls. Trustwave have a dedicated team called Spider Labs who conduct penetration testing and are very active in understanding what vulnerabilities are currently being deployed and exploited and how to protect against those. They have a great reputation of doing so, and I'd strongly recommend working with Trustwave and Spider Labs teams if that's appropriate. Can ModSecurity be configured through an API? The configuration steps that I talked about generally involve rewriting and then reloading the NGINX configuration. There are APIs. For example, ModSecurity uses an API to talk to the Trustwave rules repository in a secure fashion, so it can pull those rules down when NGINX restarts. Does it integrate well with the reverse proxy functionality of NGINX? So absolutely. And in fact, that's the most common deployment pattern. With NGINX or NGINX Plus, you can deploy ModSecurity as a reverse proxy in front of existing infrastructure. You don't need to change the web servers or application servers that are hosting your application. You deploy NGINX Plus and ModSecurity in front as a reverse proxy, and then it's capable of inspecting and blocking malicious traffic. Are there plans to inspect application responses in ModSecurity, and is there any time frame available? So we're aware of this as a shortcoming in the current ModSecurity implementation. The NGINX response substitution module is a very viable alternative for this functionality for most use cases. So for example, with response substitutions, you can look for certain patterns and map those out, mask those out. A great example is masking social security numbers or credit card numbers in responses. This is on our backlog on something to address in both the open source and NGINX Plus at some point in the future. Are there any benchmarks of NGINX with ModSecurity version 3? There are. We typically, with a fully loaded ModSecurity deployment, so using the entire CRS rules, we can handle between 400 and 800 requests per second per core on modern servers. But the performance of ModSecurity depends critically on the sophistication of the rules that you've deployed. The full CRS rules may be much more than you require for your current web application. There are many ways that you can mitigate against the performance cost of ModSecurity. The performance cost is inevitable. It comes from the huge range of rules that you're applying against traffic. And you can mitigate against that, first, by being more selective about the rules that you deploy. Second, about being selective about what traffic is then inspected by ModSecurity. And thirdly, by architecting your application from a security-conscious fashion. For example, the vast majority of the requests your application handle may relate to static content or may be routed to servers which don't need to have access to sensitive data. And what I would recommend in that case is that you partition your application to a set of clusters with different security postures. The cluster, which contains sensitive information, should be addressed by the minimum possible HTTP traffic. And then you only need to apply the strictest ModSecurity rules to that small subset of the traffic. Do I need a special subscription for ModSecurity? A user asks. So yes, if you are using NGINX Plus, NGINX Plus is accessed through a subscription. We provide keys to our protected repo for NGINX Plus. ModSecurity is not included by default with your NGINX Plus subscription. It's an additional cost option. Contact your sales representative or your evaluation representative, and we can upgrade your repo keys to give you access to the repository that does include ModSecurity. Someone asks, they make the assumption ModSecurity is not relevant for the stream proxy, and yes, that's correct. ModSecurity is purely for inspecting and managing HTTP traffic. Is there any community which provides rule sets about new security problems? So the example about Apache struts. Yes, there is. There are a couple of different sources you can go to. You can go to commercial providers, such as Trustwave, who will generate and ship their commercial rules with updates for struts, and they include rules specifically for that strut CVE. You can also work with the community through Stack Overflow, through GitHub, and through other sources to understand how users are responding to vulnerabilities like struts. And in fact, one user notes that for the rules that we shared for the Apache Struts CVE, they point out that the rule we shared was blacklisting particular request headers that had the hash command value inside. And they make the very, very valid point that as an alternative, you should seek to whitelist headers. So for example, you might whitelist the content length header, so it absolutely has to be a sequence of numerals, nothing else. Yep, that's a very, very valid point. The risk of whitelisting is that you may generate more false positives. But for the case of this, certainly for the content length header, yeah, it makes sense to whitelist that for a set of numerals rather than blacklist the hash command. NGINX are not security authorities. We are experts in NGINX itself, and the value that we bring is in building and testing and validating the ModSecurity module and providing the first level of support and interfacing with Trustwave for detailed ModSecurity support. Okay, one other note. So again, someone is asking about the options for inspecting encrypted traffic. And there are many ways to inspect encrypted traffic. ModSecurity running as a reverse proxy is the most natural way of doing so. It is possible to put SSL termination on next generation firewalls and use those to inspect encrypted traffic as well. It's also possible to inspect outgoing traffic in a forward proxy fashion by putting an internal CA root certificate on your employees' computers. Yep, it's a valid observation. That's something which falls outside the scope of what ModSecurity would be deployed for. ModSecurity is deployed for incoming traffic in a reverse proxy fashion. Okay, so folks, this has been a fantastic set of questions. I hope I've managed to address all. If you'd like more information, please do reach out to us through the website, maybe through the NGINX inquiries alias or the ask a question on the website. Thank you very much for your attendance and your attention. I hope this has been useful, and I look forward to talking to you on our next webinar. Thank you again.